All right, welcome to ABE 121. We are back in the course ABE Structures Engineering. We're in week 4 and we'll be discussing combined loadings, which is a common site in farms. We're not just talking now here of agricultural buildings. We are considering other farm structures such as tanks, okay, cylindrical tanks. We have frames, okay, whatever structural frames are needed to support whichever operations in a farm. Now let's go directly to the very first type of structure that has combined loadings, and that's the frame. And if you see in figure 2, okay, we have here a very simple frame which has 4 joints and 3 members. One or the 2 joints or the 2 points are what they are connected by a pin, and the so usually the joints are fixed or rigid, other than pinned or what we say hinged. Now the shape as shown is of a, there's no actual shape, no? But if you're going to add a portion here that has this, okay, so in essence that is something like that. We have a parallelogram or square, or a whatever parallelogram, no, not really a square. So it could be any geometric shape, including triangles. And because this is rigid over here, it's possible for these joints to rotate about that direction, or possible around this direction as well. Also same in here, okay? Could possibly rotate in any way, also in this locations. Now, because of that, the frames are not really considered that stable, but still they're widely used in bridges and other industrial buildings, also in other structures in farms. We have now number 2, a special type of frame, and it's a jointed frame, usually made up of triangular shapes. And again, the triangle is the most stable shape in engineering. And the truss is used to support loads over very long or relatively long spans. And the loads are applied in transverse direction of the length and applied only at the joints. We'll focus more on this discussion because the truss is the very the supporting structure of a building in other farm structures. Let's proceed to the parts of a truss. As you see, we have here the cords, okay, and these are the outer truss members. The very basic truss would have members composed of either, this could be wood, okay, it could be concrete, very seldom that is, steel as another common site, or of a structural component that is the truss. Now, we have also the web members as the interior truss members. And the joints or panel joints are just the joints where these members meet. Okay. There are a lot of ways to connect this members. Okay, it would depend on the material, such as wood, in metal. Okay. Now there are also the base. These are the spaces between the trusses, not shown because we are looking at a one-dimensional truss. And we have the purlins. These are the beams spanning truss to truss, and are transmitting the loads from the roof to the trusses. We have now the panels, and these are the truss portion occurring between 2 adjacent top chord joints. Okay. All right, so we now proceed to the computations of loads and trusses. Let's also take note of the the parameter, the rise. Okay, the rise would be the characteristic of the pitch. Okay, it's on the rise over the span. If you see that it's going to be the pitch, and the slope is just 1/2 of the rise over the span, or twice of the pitch. I think this is has to be corrected. I'll see and update this. Okay, but let's now proceed to the types of the trusses. And we have your two shown. We have the how and the Pratt. The others, okay, are there. You have the Fink, the Schober, Warren, and the Brace Rafter. But what I want to just focus on here is the differences of the orientation of the members. And since these are they have to be identified of the stresses if ever they were able to support. These are patented, okay, previously, so they are now a common sight in construction. Okay, the reason this is patented is because it's a matter of intellectual property that these designs are derived. Okay, and we have here the how and the Pratt, different differences in them, just merely the orientation of the inner members. Okay, the inner members of the truss. Okay. Now let's go directly to the computations. But before so, we look at the we have a review of the statically determinate truss. Okay, and what is this? Now let's proceed to the illustration of figure 4a. What we see here is a truss, okay, that has supports in points 1 and 5. And in A, we have 1 and 5 having pin connections. Okay, and since we have pin connections, we have 2 reactions for every pin, and we have here 4 reactions in total for the 2 pin connections. And if you're going to look at this figure, we have 7 joints, and the 7 joints would have given the 2 pin connections, we have 14, and given a force, okay, at 0.6, that would total 15 unknown reactions or forces. To solve for this kind of problem, since we could find, okay, we have 14 joints, so that would mean having what? We have 14 equations. So since we have 15 unknowns, we have 14 equations. That would mean a statically indeterminate structure. At the bottom, so we have now, instead of a pin connection at 5, we have a roller support. That would indicate now that we have 14 unknowns and 14 equations, since we are reducing or we are subtracting 1 from the pin connection. So that would indicate a statically determinate truss. Why is that? Because in mathematics, again, if you have a certain number of unknowns, to solve for that certain number of unknowns, you would need a number of equations equal to that certain number of unknowns. All right, let's proceed with the problem. And we have here a truss. You know, it's a truss having a roller support and a pin support in its ends, and 2 forces at points C and G, 30 kilonewtons and 70 kilonewtons respectively. What is required are the normal stresses in members AC and BD, with the cross-section of the members the same at 900 millimeters squared. So let me move over to my whiteboard so that I'll be able to compute for this and show the solutions. All right. So we have here the our whiteboard. Let's just get my pen. All right, let's try to construct the figure. I don't have the drawing yet here, so let's just draw and recreate the problem. So we have here a roller support, and that's just a single reaction at point A. Oh my, the program deleted my drawing, but let me just draw it again. Okay, so we have here, sorry, it should be the pen. So it's so it's going to be like this, right? Yeah, what happened? What happened to my drawing? Oh, it's deleting by itself. Anyway, let's try to do it again. So we have this kind of structure. And we have here points A, B, C, D, E, F, G, and H. Okay, we have supports at A and H, given the reactions there. So we have A of Y over here, H of Y, and H of X. Now, we have the distances of this what's happening to my drawing? Now the distances again, we have, okay, sorry, it's going to be uh 4 meters, 4 meters. And we have this height, 3 meters. With the forces at points C and G, this is 30 kilonewtons, and this is 70 kilonewtons. All right, we're done with the solution of this structural problem that we just showed. Okay, and we now proceed with the other structures that are having combined loadings, and these are the beam and the post. When the beam and post are combined, we have the post or column, and well, it still would have compressive stresses. Okay. Now, these are best for poultry houses, and would then have supplemental diagonal bracing, and that would introduce your combined loads. Okay. So you have last now the cylindrical tanks, and these are considered pressure vessels. So the walls are subjected to outward lateral pressure because of what? The liquid or the semi-liquid materials inside. Okay. Example, if you have water tanks, okay, that would be overhead, and the consideration of having an overhead tank would involve what? Forces, right? Forces, gravitational forces. Also, we have the silos and the grain beans as examples of these kinds of tanks. Even so, we have them carrying loads from solids or semi-solids. And again, solution would be the use of the cylindrical pressure vessel concept of mechanics of materials. Now we'll have to add the weight of the materials because that would be dead load. All right, that would be, I think, all there is in this topic. We're moving to week 5 by next session, and we're going to talk about the soil, the excavation, and then the footings. Thank you for listening, and I'll see you